Welcome back to Calculus 1. In this lecture, we will revisit a topic probably from your pre-calculus course, continuity, but using the precise language now of limits. All right, so let's think back to either your algebra course or pre-calculus course. Then, when you were talking about basic functions and their graphs, you probably had this, I'll say, definition or basic idea of a continuous function. A function is continuous if you can draw its graph without lifting up your writing implement, without lifting up your pencil, pen, chalk, whatever you're writing with. All right, again, this is a very basic idea of continuity, appropriate for an earlier course, typically algebra or pre-calculus. Then we didn't have access to the calculus concept of limits. So we're going to build on that. So here we have two graphs. The first could be a graph of a polynomial function, and that is a continuous function. You can see its graph has no breaks, gaps, or holes in it. All right. On the right, we have a function that is not continuous. This might be described, again, thinking back to your pre-calculus course, when there's kind of two different parts or pieces. We can mathematically describe this example of a function here, g of x, as perhaps a piecewise defined function. And you can see there, due to that gap in the graphs, this function is not continuous. If you were to draw this, you have to lift it up as you go from left to right, and then suddenly jump your writing implement down to where that hole is, and then resume drawing the rest of the graph. So again, this is a very basic notion of continuity, but it's no longer appropriate once we reach the level of Calculus 1 and beyond. Mathematics is actually so useful because we have very precise ideas. So what we're going to be doing right now within this lecture is redefining continuity without relying on the graph. Think back earlier, we mentioned one of our long-term goals for this course is curve sketching. Given a function's equation, being able to sketch its graph in detail. So if we don't know the graph in advance, how would we know if our function is continuous? This old pre-calc idea up there doesn't work without knowing what the graph looks like in advance. All right, now for other reasons why we want to redefine and revisit continuity is as soon as you hit the level of Calculus 1 and beyond, you start to encounter what I'll call weird functions. Let me give you one example of a weird function. This function here, f of x, it has two values, either 1 or 0, depending on if your input x is a rational number, a fraction, or if the input x is an irrational number. A number is irrational if it can't be represented as a ratio of integers, a over b. All right, so before we continue talking about this weird function, let's just take a look at two values. Let's say we were to plug in 4. 4 is a rational number. 4 can be expressed as a fraction. 4 over 1, 8 over 2 are all representations for 4. So we plug this rational number in. This weird function gives the output value 1. Now, a standard irrational number, kind of important for you if you're continuing through the calculus sequence to know these more technical properties of numbers. Pi is an irrational number. Pi cannot be expressed as a rational number, a fraction. You can get very close, but that's only an approximation. There's no exact fraction that represents pi. Square root of 2 is another frequently encountered, well-known irrational number. So if we were to plug pi into this function, since pi is irrational, this function gives you the output 0. Okay, so what's the point of introducing this weird function? Well, I actually have no idea what this graph looks like. So how would we think from the pre-calc idea if this function is continuous or not? We would need a new definition, a more precise definition, to deal with these weird functions that start popping up at the level of Calculus 1 and beyond? Well, think what we've been talking about. We've been talking so far in our course about limits. And as it turns out, we can use limits to redefine more precisely the idea of continuity. Now, this will lead us to some other ideas, but let's get into that with the basic definition now of continuity. Before I advance, we're no longer going to use this idea of a function being continuous based off of being able to draw its graph. We're going to give a new definition in terms of limits for continuity. With that out of the way, now that I'm getting you pretty excited about this new definition, I can tell, let's get to this new definition of continuity. All right, and there it is. We're defining here what it means for a function to be continuous at x equals a. And this definition is incredibly short. And the definition, I'll read it, is a function f is continuous at x equals a if the limit as x approaches a of f of x equals f of a. So basically what this is saying is a function f is continuous at a number a if the limit value equals the function value. All right, now I'll confess this looks very simple. The definition, we can just write it as a single short sentence. But oftentimes in mathematics, something that seems simple might be incredibly dense. There might be a lot of ideas that go into one simple definition or idea. And this is certainly one of those. So this simple definition actually says quite a lot. So let's start to unravel what the different kind of ideas that go into a function being continuous at x equals a, what that means now with this limit definition of continuity. All right, so there's three typical things that I want to point out. A Calculus 1 course at the university and college level should be getting into this detail. All right, and what this simple definition really says, there's three things that we're going to point out, is first, if a function is continuous at x equals a, the first part is that f of a, the function value, must be defined. All right, just think, some function values could be undefined, like division by 0. All right, a second condition that this definition says, but not outright, is that the limit as x approaches a of that function f of x must exist. Well, just think, do all limits exist? Nope. We've seen a few examples where the limit, or two-sided limit, doesn't exist because the individual one-sided limits, while they might exist, they could be different. And if your one-sided limits are different, then the two-sided limit does not exist. So like above, not all function values are defined. Not all limits exist. All right, the third thing that this definition for continuity says is that these two quantities, the function value and limit value, must be equal. All right, and that's actually quite a lot that goes into making the function continuous at x equals a. There has to be a function value, there has to be a limit, and the limit and function values have to be equal. All right, now the standard terminology is if any of these conditions fail, then we say the function has what's called a discontinuity at that point x equals a. And what we're going to be getting into is within the language of limits, this definition is going to lead to three types of discontinuities. There's actually quite a large number of discontinuities throughout mathematics, but we're going to introduce the simplest and most encountered types of discontinuities in this lecture. So before we advance, maybe pause just to copy down those three things that go into making the definition of continuity hold. We'll be referencing them. Make sure you number them. Property 1, 2, and 3, we'll be referring to them. I'll have them on the next screen, but might be good just to have them in front of you within your notebook. I'll give you a few seconds if you want to pause. All right, so let's advance. we're going to get into detail about what these three standard, most common types of discontinuities are. And it's going to be in terms of one of these conditions, 1, 2, or 3, failing. All right, so here we're going to look at those three common types of discontinuities. If you continue into higher level mathematics beyond the calculus sequence, you'll encounter the kind of more weird types of discontinuities. All right, so far at the top of the screen here, that was just everything from before, writing the limit definition of continuity. The limit as x approaches a of f of x equals f of a. And then we have those numbered properties from before, the three properties that go into that limit definition of continuity. All right, the first type of discontinuity, and it's probably the simplest, is what's called a removable discontinuity. Now, you might have encountered graphs like this in your pre-calculus course, graphs that had holes in them, but we'll be kind of going into more detail with them now. All right, and a removable discontinuity is where condition 3 fails. In other words, there's a limit value, the limit exists, there's a function value, the function value is defined. It's just that the limit and function values are not equal. They're different. Graphically, what that looks like, over on the right here, we have one of a lot of different possible graphs. This is just a simple one. What a removable discontinuity looks like, it's pretty much a basic idea of a continuous function. It's just that we took one value, one point on the graph, and removed it and put it somewhere else vertically above. And that's what the hole indicates. There is no point there, or y-coordinate. The y-coordinate is up where the closed point, the kind of black dot is drawn. All right, so this is what a removable discontinuity looks like. Before we move on, make sure we realize we're not going to be relying on the graphs. We want to rely on that statement right to the left there about condition 3 failing. A removable discontinuity occurs when the limit value does not equal the function value at a certain x value. We'll see that in some examples. All right, the second type is what's called a jump discontinuity. And this is where condition 2 fails in a particular way. There's kind of several possible ways for a limit not to exist. The simplest way that we've been encountering a lot for a two-sided limit to not exist is when the individual one-sided limits from the right and left are different. So here, we'll define a jump discontinuity to be the precise case where the left and right side limits, or limits from the right and left, are different. Now, this is a familiar graphical feature that you've probably been encountering throughout your pre-calculus course. That's when you're typically introduced to piecewise defined functions. And you saw those in your pre-calculus course to prepare you for now. So that way we're not kind of seeing these things coming out of nowhere. So pretty much everything from your pre-calculus course does get used in a standard Calculus 1 course. Think of your pre-calculus course as a Calculus 1 boot camp. All right, so this is one example of a jump discontinuity, possibly for a piecewise defined function. We'll see in a following example a question involving a piecewise defined function. All right, the third and final standard type, or most common type of discontinuity, is what's called an infinite discontinuity. And I'll confess, we're really just repackaging the idea of a vertical asymptote in the language now of calculus with limits. So pretty much an infinite discontinuity is a vertical asymptote. Now we're calling it an infinite discontinuity because condition 1 is going to fail. And that means the function value is undefined, but more particularly, when function values are undefined, think division by 0. We saw examples earlier in previous lectures within our course so far where plugging in gives division by 0, but the limit works out to be positive or negative infinity. So we're going to make the connection a typical way for a function value to be undefined, division by 0. Earlier we said division by 0 usually corresponds with limits to being positive or negative infinity. So an infinite discontinuity, we'll define it to be where we have a limit to a from either the right or left being either positive or negative infinity. As long as there is one of the two one-sided limits being positive or negative infinity, that's enough for us to say the function has an infinite discontinuity. Graphically, an infinite discontinuity looks like a vertical asymptote. All right, now these are the three standard types. If you continue into higher level mathematics, you'll see other types of discontinuities that aren't removable, a jump discontinuity, or an infinite discontinuity. But these are the standard three that we'll have you learn about within our Calculus 1 course. All right, now again, before we advance to some examples, maybe pause just to copy some of these conditions down, the definitions here for a removable, jump, or infinite discontinuity. Each discontinuity has a particular property of limits involved with it. A removable discontinuity has the limit value not equaling the function value. A jump discontinuity has the left and right hand limits, or limits from the right and left, being not equal. And an infinite discontinuity is pretty much any value for x when we take a limit from the right or left that gives positive or negative infinity, an infinite limit. All right, when you're ready, we'll get to the first real example. All right, let's get to example 1. This is an example just to show you how using ideas for limits, we can then construct properties of what the graph might look like. Now, again, I'll confess, you could probably answer this question if you feel comfortable sketching a piecewise defined function, which we have here. F of x, as written, is a 3-piece piecewise defined function. We're not going to do that. We'll mention that at the end. What we're going to try to do, since curve sketching a graph is one of our long-term goals, we want to rely now on this new limit definition. And that's what we'll start to learn here. That's the kind of end goal with this example, to see how limits then tell us something about the graph rather than relying on having the graph in advance. Okay, the question is just asking us to find and classify the discontinuities of this function. Now, we're going to try to think of some kind of ideas just to get us started. This is a piecewise defined function. It has a different formula on a different interval. And from your pre-calc course, you probably saw that piecewise defined functions typically have jump discontinuities, graphs that have a gap in them. All right, so, well, let's just keep that in mind, that we're expecting possibly this function to have jump discontinuities. Let's take a look at the 3 individual pieces or functions involved. We have y equals negative x, y equals 2, and y equals x minus 1 squared. Now, y equals negative x and y equals 2, those are equations of lines. Straight lines from your algebra course are continuous. They have no breaks, gaps, or holes in them. All right, the last function, y equals x minus 1 squared, that's a parabola that is shifted 1 unit to the right. Recall horizontal transformations from your pre-calculus course. X minus 1 inside the function actually causes or induces a shift to the right by 1 unit. All right, so why are we mentioning this? All 3 of our pieces, y equals negative x, y equals 2, and y equals x minus 1 squared, individually are all continuous. How could this piecewise defined function then have discontinuities? Well, we might start to take parts of these three functions and then combine them together so that way they have discontinuities. So where should we look? Individually, all three pieces are continuous. Typically, for a piecewise defined function, we're going to check what I call the transition points. The points where the different formula transitions from one to another, or where the points where the interval changes. All right, so here our transition points are x equals -1 and x equals 1. What we're going to do, since we expect jump discontinuities were defined by the right side and left side limits being different. So let's pick one of them. Let's go with, let's say, x equals 1, and let's check the limits from the right and left to x equals 1. Now, this piecewise defined function has us looking at an interval just to the right and left of 1. And to the right of 1, values of x that are greater than 1, the function, the formula, is x minus 1 squared. That's applicable when your value for x in the definition is greater than or equal to 1. Now notice just to the left of 1, where your values for x are a little bit less than 1, that puts us in a different interval, the interval for that function up there, from -1 to 1. On that interval, values of x less than 1, the function f of x equals 2. So what seems to be a complicated piecewise defined function is actually very simple when we're evaluating a limit from the right or left. On each interval on one side, the function has only a single formula. So let's check first the limit from the right. Notice as we approach 1 from the right, values of x greater than 1, we can use the function f of x as the formula x minus 1 squared, since our x values are to the right of 1. All right, that function x minus 1 squared, well, we can just plug in. It's a polynomial, and if we plug in 1, well, that evaluates to 0. So the right-hand limit, or the limit from the right, is 0 here. All right, by itself, we can't make a conclusion about there being a jump discontinuity. So let's check the limit to the or from the left of 1. All right, and now we're just approaching 1 from the left side, where we're on a different interval, and we use now the formula f of x equals 2. And that's a constant function. The limit is just going to be 2. So what we see is our limit from the right is 0. Our limit from the left is 2. 2 and 0 are different. The right and left side limits are different. That means we have a jump discontinuity at x equals 1. Now again, we could have used the graph, but we're trying to not rely on that, rely on the graph, since that's going to be a long-term goal for our course. All right, now that you get a sense for maybe how to work with piecewise defined functions and individual limits from the right or left, maybe give yourself a minute to try seeing what you can make a conclusion about the other transition point, x equals -1. We'll check in about a minute. All right, let's go ahead and check what's going on with this function at x equals -1. It's very similar. We're going to check a limit from the right and a limit from the left to -1. And what you should find is your limit from the right, as you approach values of x equal to -1, that right-hand limit or right side limit comes out to 2. As we approach -1 from the left, just be careful. X is approaching -1 from the left, but while you're on the left of -1, we use the formula f of x equals -x. So just be careful. We're going to plug in x equals -1 to the formula negative x. There's a negative that cancels. We get here +1 for the limit. Again, we see the right and left side limits are different. That's enough for us to conclude x equals -1 is also a jump discontinuity. And that concludes the question here. We have two discontinuities, both of which are jump discontinuities. They occur at x equals 1 and x equals -1. All right, now that we've answered this question without relying on the graph, let's take a look at the graph, which should confirm this. All right, and if you were to sketch this in detail, again, as you were probably asked in your pre-calculus course, we get a graph that looks like this. We have the basic graphs of -x, the basic graph of y equals 2, a horizontal line, and then a basic graph of x minus 1 squared. All right, and notice from the intervals, either including with inequalities less than or equal to or greater than or equal to versus the strict inequality on the middle interval, we have some open and closed points on the graph. All right, and again, this graph confirms there's jump discontinuities at -1 and 1. There's gaps in the graph there. All right, let's get to a second example. Let's find and classify the discontinuities now of this rational function, fraction, f of x equals x divided by x minus 2 squared. Maybe pause the video and give yourself an attempt. Start thinking about those different types of discontinuities, what might happen involving division. We'll check in maybe about 2 minutes. All right, now maybe you made an attempt, maybe you feel stuck, that's okay. This is kind of a transition going from old ideas of continuity to now new ideas with limits, so it's okay to be stuck and feel confused. All right, so the hint I was giving is we have a function defined as a fraction with division, and recall there's a problem when we divide by 0. Now if we take a look at our denominator, x minus 2 squared, this denominator equals 0 when x equals 2. All right, so there's a value of x for which our denominator becomes 0. All right, I want to make the connection just so you start to see the difference with, let's say, division by 0 and what we mentioned earlier in our previous lecture about an indeterminate form, 0 over 0. Division by 0 and 0 over 0 are different. 0 over 0 in indeterminate form points to trying to use an algebraic trick. Division by 0, that points to the limit likely being infinity or negative infinity, an infinite discontinuity. So let's check limits as x approaches 2. We can do so from the right and left. You'll find both limits approach positive infinity. If you're not sure, just plug in a value close to 2 on either side, and you should find you get a positive number in each case. So both limits to the right and left of 2 approach infinity. It's enough just with one of them, one of those one-sided limits to be infinity, for us to say x equals 2 is then an infinite discontinuity. And that's it for this example. So this function has a single discontinuity at x equals 2. Graphically, this would look like a vertical asymptote. Now, before we advance to the next part, just to review some pre-calculus ideas, this function becomes undefined when x equals 2. What that would mean for the domain of this function, the domain of this function would then be all real numbers except 2. So we'll reference that in the next example. The domain here is not all real numbers. the domain for this function, x divided by x minus 2 squared, is all real numbers except 2. All right, with that in mind, let's kind of get to the next part. Now that we've worked through a few examples and start to get a sense for different types of functions and discontinuities, removable discontinuities, jump discontinuities, and infinite discontinuities, and using limit laws, we now have enough tools to kind of logically prove a bunch of different functions that are continuous on their domains. So we're going to keep that in mind. Whatever the domain for these specific functions are, we'll be saying they are continuous on their domains. So in other words, on their domains, for intervals for which the function is defined, the graphs are going to be continuous. They will have no breaks, gaps, or holes on their domains. All right, now think back to your limit laws, basic powers of x. We can start combining them together to get polynomials. Now, before I put all the different types up on the screens, I'll say pretty much every function you encountered in your pre-calculus course was continuous. Polynomials are continuous. Rational functions are continuous on their domains. Radicals are continuous. Exponentials and logs, e to the x and natural log of x, are the important ones for calculus. And then your 6 trigonometric functions are continuous on their domains as well. Pretty much every basic function that you're familiar with, the simple functions, none of those weird functions like we mentioned in the intro, those simple basic functions are continuous on their domains. All right, that's good news for us since continuous functions have some very nice properties which we'll continue to use throughout our course. Now we can, with this basic list of functions, start building up other continuous functions by using some basic operations. Now real numbers have 4 basic operations: addition, subtraction, multiplication, and division. I guess you could say exponentiation, but that's really repeated multiplication. But functions have a 5th operation: composition, plugging a function into another function. So if we take any of these 5 different types of functions and then combine them in these 5 ways by adding, subtracting, multiplying, dividing, or plugging one of them into another, the end result would be also continuous. All right, so from here we can build up a rather long list of complicated functions that would be continuous. Now, since we're talking about continuous functions, let's take a look at an extremely useful theorem that we will be using throughout the course. We'll recall this when we need it. It's basically a theorem on limits that pertains and relates to composite functions. All right, and the goal is, let's say we have a limit involving a composite function, the limit as x approaches a of the function f of g of x. Some students would call that fog of x, since it looks like the letter O, but that's the composite function symbol, f of g of x. Make sure you're comfortable with that notation from your pre-calculus course. All right, what this theorem says is if we have a continuous function on the outside, so the outer function f is continuous, what we can do to evaluate the limit of this composite function, provided the outer function is continuous, is we can bring the limit inside and basically evaluate this composite function limit by taking the limit of the inner part, the limit as x approaches a of g of x, which is L, and then we just plug L into the function, the outer function f, to get the limit here, f of L. This will be useful. We'll recall it when needed. There's likely just a few examples scattered in the homework asking you to apply this, but we'll recall it when we need it for kind of a new topic. All right, let's kind of conclude with a useful result called the intermediate value theorem, or IVT for short. This is extremely useful for continuous functions. And the setup is, let's say we have a continuous function on a closed interval a to b. Now, if we pick an intermediate value, which we'll just symbolically call z, so z is somewhere on the y-axis between f of a and f of b, then if provided the function's continuous, that intermediate y value, which we're writing as z, has a corresponding x value in the interval from a to b. We're going to call that x coordinate c. All right, the precise statement of the intermediate value theorem is here. So basically it just says if we have any intermediate value z between f of a and f of b, then there exists an x value c such that f of c equals z. All right, this is the intermediate value theorem. Let's take a look at a really quick example, kind of useful for different problems that appear in calculus. We're going to show that this function has a root within this interval 1 to 2. Now, a root also is known as a zero or x-intercept. A root, zero or x-intercept, is an x-coordinate or x value such that f of c equals the y or function value 0. We're going to think of 0 being the intermediate value here. So what we want to do is find something that is a little bit bigger than 0, positive, and something a little bit less than 0, a negative, and then we could apply the intermediate value theorem to conclude there's an x value such that f of c equals the intermediate value 0. All right, as it turns out, the calculations are rather simple. The function here, f, is a polynomial. Polynomials are continuous on their domains, all real numbers. If we plug in the endpoints of that interval, 1 and 2, you'll get -13 and +8. And 0 is directly between a negative and positive. 0 is the intermediate value. So since we have a continuous function and an intermediate value between that negative and positive, f of 1 and f of 2, well, we get the conclusion there exists a number c within the interval 1 to 2 such that f of c equals 0. So what that means here is that there is a root or solution to the equation f of x equals 0 within that interval 1 to 2. Now this is useful within the level of calculus because you can start to get into some programming questions if you're familiar with computer programming that ask you to write a simple program to calculate the roots. So with what might be called a root finding algorithm. Now if you were to apply that, as I did here, you'd find that the x-coordinate c referenced here, that's between 1 and 2, for which f of c equals 0, it's about 1.86672. That's using some approximation methods, a root finding algorithm, which confirms what we have here. The intermediate value theorem in mathematics is called an existence theorem. It tells us that this number, x-coordinate c, exists. So now we can apply our algorithm to go forth and find it. It comes out to be approximately 1.86672. All right, and that's it for our lecture here on continuity.